So if we look back at everything we've been talking about over the last few sections, we started by talking about Lewis dot diagrams. Lewis dot diagrams then took us to our electron geometries, which brought about our molecular shapes, and finally we ended talking in the last section about polarity. Now, why were all of those steps and sequences important? Because as we start to see the structure of molecules and the shapes that molecules take, then what we start to find is that we can see how those molecules will interact with other molecules or atoms of the same substance and how they will start to hook up and bond with one another. So in this section, we're going to be taking everything we've spoken about, molecular shapes, polarities, and we're going to use those things to talk about this idea over here known as intermolecular forces, or the attractions that exist between different molecules of the same substance. And we're going to use those intermolecular forces to then be able to predict what is the state of matter that we will then most likely find said substance, right? So if you recall, at the very beginning of this year, we talked about we had solids, we had liquids, we had gases. Now those are the three most fundamental states of matter. We're not going into plasma and other more theoretical states. What we want to do is keep it as simple as possible for right now. And let's think in terms of we're at room temperature. Well, at room temperature, we're more than likely going to find matter in either a gaseous, a liquid, or a solid state. And so what this section is going to be all about is answering the question, well, why? Why do we find a certain substance as a gas but another substance as a liquid? Why do we find a certain substance as a liquid but another substance is now a solid, right? And in order to answer all of those questions, we're going to have to look at, as we said earlier, this idea of intermolecular forces, or the attractions that all of these molecules have with one another. So when we talk about intermolecular forces, there are three distinctive types of IMFs, intermolecular forces. I have them listed over here, right, according to strength of the intermolecular force. So the weakest of all of them is known as London Dispersion Forces, also known as LDFs. You'll commonly see that abbreviation. Now, some textbooks will refer to London Dispersion Forces as van der Waals, okay, so V-A-N-D-E-R, and then Waals, W-A-A-L-S, so van der Waals forces. Same thing, it's London Dispersion Forces, and these are the weakest. I'm going to paint with a very broad roll brush first, and then we'll go into more detail on each of these. So when I talk about London Dispersion Forces and I say they're very weak, the way you can think of it is that every single substance, right, every single atom, every single molecule, whatever you want to call it, all substances have LDFs, London Dispersion Forces, meaning all substances will, to some extent, have some type of attraction amongst its particles to other particles, okay? And that's everybody, every single substance. So this can be everything from helium gas to diamond, to water vapor, to carbon tetrachloride, to sodium chloride, you name it, whether it's crystalline solids, whether they're gases, liquids, whatever. Every substance has, to an extent, London Dispersion Forces. The next one on the strength category is going to be the one known as Dipole Dipole. Okay, now that is typically a lot stronger, than London Dispersion Forces. And finally, the strongest of all of my IMFs are known as hydrogen bonds or hydrogen bonding. Okay, now, a little note about IMFs, because usually when I talk about this, a lot of students will go, so are IMFs as strong as, let's say, bonds within a molecule? And more than likely, no. Okay, so here's my little analogy. Let's go back to the last section when we were talking about covalent bonds. We talked about single, double, triple bonds. Let's start off with the easiest type. Suppose, if you will, that a covalent bond was literally nothing more than a handshake between two different atoms, right? Now, if I were to sit there and I were to reach for it and I were to go shake your hand, sake of argument, right? The attraction or the hold that we would do when we shook hands would be a very tight, solid hold. I'm going to refer to that as my single bond. Again, not that it is, but just kind of so you get the idea. Now to put that into perspective, if a single bond were a firm handshake, then a London dispersion force would literally be if we went and we touched pinkies. Now you're sitting there and you might be thinking to yourself, well, this doesn't seem like a very strong hold touching pinkies. And the answer is it really isn't. But in theory, if I close my eyes and I kind of move one hand, the other one can feel which way it's moving and we're okay. The problem is that if I move too fast, I suddenly break or overcome that London dispersion force. And that's a good analogy for it. London dispersion forces typically are very weak, right? So it's like these very tight, it's these very light attractions between particles. They're not going to serve a whole lot of like the glue that keeps things together, usually. I keep saying that word because, of course, we can have exceptions to this. Now, if that was a London dispersion force, a dipole-dipole is going to be a little bit of a coupling. So imagine here are my two little fingers, right? And instead of just having them touch like I did a moment ago with the London dispersion force, in dipole-dipole, it's almost like they're going to couple like it were a train car. So kind of see how I'm curving my fingers a little here, right? So this is what's going to happen. That now it's a little bit tighter of a hold, right? So we're kind of like hooking into one another like this, right? So we're hooked in, and what's nice about that is that now I can pull one way or pull the other way, and I do have a lot more attraction in the bond. Yay! Right? That's good. But as you can kind of imagine, it's not like this is that strong of a hold. So yes, if I start moving around, I'm holding, until I lose track, right? So a dipole-dipole attraction is going to have a stronger hold, a stronger pull, but again, that is, as we've spoken into, to an extent. And finally, last but not least, is our hydrogen bonding. Now again, typically, hydrogen bonding is going to be the strongest of my three intermolecular forces, right? But it's usually not necessarily as strong as a single bond. So the way I describe it is that now we're going to do a little pinky swear, right? So here's my little pinky swear between my two hands, right? And this is going to be what my hydrogen bond is. It's now I'm just doing a little pinky swear. They're holding on to one another. Yes, this is a much tighter hold than anything else that I've done, but am I going to sit there and be able to pull you off in one direction with a pinky swear? And the answer is of course not, right? So again, hydrogen bonding, a lot stronger than anything we've talked about, but it is typically, emphasis on typically, not going to be stronger than a single, double, or triple bond. And the way I kind of differentiate them is that intermolecular forces are the forces or attraction between different molecules. But if I'm talking about single bonds or double bonds or triple bonds, then in that case, I'm talking about within molecular forces. And these intramolecular forces, like single bonds and double bonds and triple bonds, ionic bonds, right? All of these are going to typically be much stronger. It requires a lot of work to break intramolecular forces, right? It requires a lot of work to break a single bond. It takes a lot of work to break an ionic bond, right? So that takes a lot of energy, as opposed to between two different molecules. Again, these are my intermolecular forces, and IMFs typically are going to be much weaker than the intramolecular forces. So in the next episode, we're going to start by looking at our three distinctive intermolecular forces. The first one that we're going to look at is right over here. This is going to be my London dispersion forces, and we're going to look at how are they formed, right? How strong are they, and what occurs when a London dispersion force is in play. And we're going to move from there into dipole-dipole and finally hydrogen bonding. Once we know our three intermolecular forces, we'll then use all that information to finally predict, and this is the important part, predict what is going to be the state of matter then of a given substance. And again, this is a little bit of guesswork, but by knowing the molecular shape, by knowing the polarity, we then can apply the proper intermolecular force, and now we can start to say intelligent things as to how that substance will probably interact with other atoms or molecules of the same substance. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.